Now we're going to talk a little bit more about some issues more related to classification and discrimination, but still important to talk about as well, involving the types of errors you can make and the cost of errors and the base rates. So in classification analysis, when you have two groups, there are two types of errors to consider. There's incorrect classifications for group 1 and incorrect classifications in group 2. These are often referred to as false negatives and false positives. One thing we haven't really considered yet to this point is whether one type of error matters more than another. So in our example so far, maybe a false negative where we classify a sick person as healthy is much more costly than a false positive. In a false negative situation, you might say, you might clear someone to enter a crowded space, but then if it turns out that they're actually sick, then that they might get a bunch of other people sick, and that might be very costly. So we can account for this by adjusting our classification rules so that it's more liberal about assigning people to being sick and more conservative about assigning people to healthy. We call this a cost function. So to incorporate our cost function, we still compute the discrimination function the same way. So we do the same discriminant analysis, but now to do our classification, we check whether the y-hats, the estimated values, are greater than the log of the ratio of the costs, rather than to 0. So one way you can also think about this is that we're saying when we don't include a cost function, we actually really are including a cost function. We're just saying that the two types of errors have equivalent costs. So when the cost of a false negative is the same as the cost of a false positive, the log of their ratio is equal to the log of 1, which is 0. So if the two costs are not equal, we're just saying we're willing to make a few more total errors because certain types of errors are more costly than others. So the LDA function doesn't have a direct way to accept the cost function, but what it does have is a prior argument that accepts probabilities, which can function similarly. So to convert our cost ratio to probabilities, we compute the ratio of the costs divided by 1 plus the ratio of the costs. So this will give us the cost of being in group 2 converted to a probability. And then the cost of being in group 1 is 1 minus that probability. And then P1 and P2 can be entered into the prior argument. We could also do this the other way, just by flipping the ratio around and getting P1 first and then getting P2 as 1 minus P1. The results would be identical. We just usually focus on group 2 since we usually code negative as 0 and 1 as positive. And so we're treating positive as group 2. So let's say our cost of false positive is 3 times greater than a false negative. So first, let's double check what our factor levels are. So this is how we want it. We have healthy, which would be negative in group 1, and sick, which would be positive in group 2. So all good there. So we convert our cost ratio to a probability by taking 3 over 1 divided by 1 plus 3 over 1. So that's 0.75. This is the cost for group 2, sick, converted to a probability. And for group 1, we just take 1 minus 1 minus the probability that we got. And so notice that this ratio, 0.75 to 0.25, is the same as the original ratio of 3 to 1. So we can, of course, do all of this in R. We can first code our cost as 3 for false negative as 3 and false positive as 1. I actually just wound up writing them in here. I should be using, just to make my code reproducible, reusable, I should be entering the objects I create down here, because I will reference these again later, so that's why I created them. But either way, it doesn't matter. So then you take the ratio of the false negative cost to the false positive cost divided by 1 plus false negative cost divided by false positive cost. And that gives us our prior. And then for since this is the prior probability for group 2, in our prior argument, we take 1 minus the false negative prior and then the false negative prior for the second probability. So this is the prior probability for as a cost converted to a probability for group 1, and this is for group 2. And then we can once again get our classification from this function. So if we look at the contingency table here, we see that we're making more total errors than we did when we didn't include a cost function. So we're making 48 total errors as compared to 36, but fewer of them are sick people who are actually sick who are classifying as healthy. So we have fewer false negatives, but more false positives. And so here is the original plot. So this is without the cost function. So this is the plot that we saw last time, just for reference. And now we can see what happens when we've incorporated the cost function. So we see more of the points have been classified as sick, so there's more red, and there's a few more red X's, but many fewer. I mean, there's quite a few more red X's, but there's very few blue X's now. So there's very few false negatives. So another thing to consider are what we call base rates. So by checking our discriminant function against 0, we're saying that we expect the population to have equal numbers of observations in both categories. So we're saying essentially that we believe our design is balanced, and this is the case in our running example so far. We have chosen to set it up this way, so we have 100 of each in that example. But in reality, this assumption will not always be true. Unless you're doing a really well-controlled experiment, often you're going to have slightly different sample sizes, sometimes very different sample sizes. And so this will affect the expected proportion of members in each group. And this is called the base rate. In Bayesian terms, the base rate is called a prior. And so by not setting a prior, we're saying that we have a flat prior, which means we can, before considering any other factors, we're saying there's a 50-50 chance a participant belongs to one of the two groups. So we can incorporate a non-flat prior. We can incorporate our base rate by similarly to what we did with the cost function. Instead of comparing to 0, compare to the log of the ratio of the probability, the proportion, the probability of being positive to the probability of being negative, according to our prior probability or according to what we believe the base rate is. So once again, we can note that when these two are equal, they're both equal to 0.5. And so that means that the log of 0.5 over 0.5 is log of 1. And so that's once again 0. So by checking against 0, we're implicitly saying we expect the prior probabilities to be equivalent. So we can again use the prior function in LDA to specify our prior probabilities. And so remember, double check in R what order the categories go in. So that means for the prior argument, we enter the base rate or the prior for being healthy first, and then for being sick in that order. So in this case, whereas this was a little complex when we were incorporating cost, the LDA function is smart. So it's going to do this for us. So by default, it's going to set up the prior probability to be the actual proportions of group membership in the observed data. So when we have 100 of each group, the prior was 0.5 for both groups. So this is because the data set was balanced. So here's an example where the data is not balanced and perhaps more realistic if we were just drawing randomly from the population. So this file has 500 observations, but 450 are healthy and 50 are sick. So only 10% of these observations are people who are actually sick. So let's see what happens if we use the LDA function with the default prior here. So here I'm going to load in my data. We see that we have 450 healthy, 50 sick. And then I'm going to run my linear discriminant analysis, my LDA, and you can see that the prior it matches that proportion. So it's the proportion of observations in both categories. And so we can once again look at the contingency table for this classification. And so we see pretty appropriately, it's classifying most of the people as healthy, and in most cases there are very few errors, and then very few people as sick, with again a few errors. So it it did a pretty good job of minimizing the error here, minimizing the total errors. And so I can once again plot this classification like I did before from just based on this data and based on the classifications. And so we see this is what our classification wound up looking like. So here, many more of the total observations are blue because that was just the case. And then there are very few that are red. And then there are, as before, most of the errors are around here in the middle, where the separating line is. So we can also check what would happen if we used a bad prior in this case. So if we just manually entered a prior that was not very good. So in this case, I'm going to have 0.5 and 0.5, which is the prior from when we had the balanced data. And so now we see if we check the contingency table, before we made only 25 total errors, and now we're making 94. So we're making a lot more errors with this bad prior. So we generally want to leave the actual prior probability to be the default, unless we have a good reason not to, such as incorporating the cost. So here we see this is what happens with the bad prior, and here you see we have quite a few false negatives or false positives. Red X's are false positives. So we're making a lot more errors among people who are actually healthy. So while R is smart about priors, when you fit the models themselves, there are cases where we have a non-flat prior and we want to combine it with a cost function. So when the prior is flat and we want to use a cost function, we can just think about the cost function. When we have both an unbalanced data set and a cost function, we have to get a little fancy again. So the way we evaluate when we have both a cost function and prior probability or an unbalanced base rate is we multiply the cost ratio, so by the ratio of the probability. So you're going to want the false negative to correspond to the probability of positive, and the false positive to correspond to the probability of negative. You could, of course, flip this around and do it that way. That would just be sort of switching just the interpretations of things. But this is traditionally how you'll do it because you're considering the reference class to be, when you consider the reference class to be positive, or the reference class to be negative and the coded one class to be positive. So if we want to combine our cost ratio of 3 to 1 with our prior probabilities of 0.1 and 0.9, we're going to start by multiplying out those ratios. So we have 3 divided by 1 times 0.1 over 0.9. So that's going to give us 0.3 over 0.9, which is going to give us 1 over 3. And then we do the same thing we did before. So we're going to convert this to probability by taking 1 over 3 divided by 1 plus 1 over 3. So 0.25 is our new combined prior and cost for group 2, and then 1 minus 0.25 is 0.75. That's our combined prior and cost for healthy. And so these are the values we're going to enter into our prior argument. So as the first thing I'm going to do here is I'm going to get my base rates. So I'm going to get my base rate for sick, and this is going to be my prior for sick and my prior for healthy, just by taking the proportion of observations in each category. Then I'm going to multiply this by my cost ratio. So this is the cost ratio we had before, the ratio of false negatives, cost of false negative to cost of false positive, times prior sick over prior healthy. So that's going to give us that 1 over 3 combined ratio of prior and cost. Then I'm going to convert this into a probability. So I'm going to take the prior cost ratio divided by 1 plus the prior cost ratio. That's 0.25. And so 1 minus 0.25 is 0.75. So again, 0.25 to 0.75 is the 1 over 3 ratio, just converted onto the probability scale, the unit scale. And so then I'm going to enter, once again, the probability for group 1, which is 1 minus the prior plus cost for sick, and then the prior plus cost for sick. So that's my new prior. And then I do, once again, you can do my classification. And so essentially what we're saying here is, again, we're willing to make a few more errors to be a little bit more conservative about false negatives. And we're also, at the same time, making sure to consider our actual base rate. So this satisfies both conditions, the base rate and the cost function. And so there is the plot. And so this is the plot that combines both the base rate with as the prior, and then the cost as well at the same time. And so one thing to keep in mind is all of this is about classification. It doesn't actually change the discriminant function. All it's doing is changing the criteria by which we classify. So the coefficients for the discriminant function are the same no matter what you enter for the prior argument. The prior argument is just saying, this is what my classification criteria is going to be. So it's by default, it's going to be the classification criteria is 0. And here we're saying, or it's greater than equal to 0. Here we're saying it's something else. It's not 0.